Hey there, y'all. Today we're going to look at 2.7 on compound inequalities. And in this section, the objective is that you'll be able to solve and write compound inequalities. And we're continuing under the standard that we've been working on most of this unit, AREI3, on solving linear equations and inequalities in one variable. And so we first need to talk about what is a compound inequality. Well, a compound inequality is an inequality involving the words and or. And so I want us to think about those two words for a minute because we use them in English all the time. The word and means that we're going to do both, right? So let's say I use this phrase, I want to go to the beach and I want to go to the movies. That means we're going to do both, right? I want to go to the beach and I'm going to go to the movies. So, we're going to do both, right? We'll go to the beach and then afterwards we'll go to the movies. And so it's both. But the word or, when we're talking about it in a sentence, I want to go to the beach or I want to go to the movies. When we say it like that, it's a choice. I'm going to go to the beach or I'm going to go to the movies, but I'm not going to do both. And we call that an exclusive or, meaning I'm going to do one or the other, but not both. And so we might say that it's this or that, right? I'm going to do this or I'm going to do that, not both. But we do have other cases where we talk about an inclusive or. And so an example of that would be, would you like mustard and ketchup on your hot dog? Excuse me, would you like mustard or ketchup on your hot dog, right? Well, we could ask for both to be on the hot dog, right? We could want mustard and ketchup. I mean, I like both on my hot dogs. And so when we talk about an inclusive or, it means both. So in math, when we talk about or, it is that inclusive or that it could be this or that, or it could be both. And so let's look at a couple statements and see what that means to these problems. And so we have the graph of a compound inequality with the word and is the intersection of the graphs of the inequalities. Again, the graph of a compound inequality with the word and is the intersection of the graphs of the inequalities. And so when we talk about the word intersection, what does it mean to intersect? So we think about roads, right? If we go to Highway 1 and Highway 601, they intersect somewhere, right? Or if we talk about I-20 and I-26, it's an intersection of those two interstates, which we call malfunction junction, right? But it's an intersection of those two. It's where they meet. And so we're going to look at this example. So we're going to look at x is less than 5 and x is greater than or equal to 2. And so I've drawn three number lines here, and we've numbered them from 0 to 6. And we're going to draw on the first number line just the first part. X is less than 5. So what would that graph look like? Well, at 5, I'm going to have a circle. And what values are less than 5? Is 4 less than 5? Or is 6 less than 5? It's 4, so I'm going to shade towards 4. And so all my shading goes this way forever, right? And we draw on that arrowhead. And then we're going to do the same for x is greater than or equal to 2. What do we put at the 2? We put a dot. And where's that shading going to go? Is 1 greater than or equal to 2? Or is 3 greater than or equal to 2? It's the 3. And so my shading will go towards 3, and we look at this. Now, when we talk about intersection, we're talking about where they meet. And so I've used blue and red intentionally because when red and blue meet, what do they make? Red and blue make purple. And so we want to see when we take these two graphs and we squish them together, where do I get purple? That's what matters. Now, anywhere I've got a dot, that dot will stay. Anywhere I've got a circle, that circle will stay. But what's going to happen in the middle? Red and blue make purple. And so the purple is this little region right here. Now, what are the solutions of this? Well, it's any value that could work for both, right? So if I pick 3, 3 is less than 5, that works. And 3 is greater than or equal to 2, so it works for both, right? Because again, and means it has to be what? Both. It cannot just be one or the other because it's and. It's got to work for both to be a final solution to this. Now, what are numbers that are not going to work? Well, like 1, right? 1 works for the first statement. 1 is less than 5, but the problem is that 1 is not greater than or equal to 2. It doesn't work for both. That's the key to an and problem. It's got to work for both. So now let's go look at OR statements and see what it does. So with OR statements, here's our statement on what an OR is. The graph of a compound inequality with OR is the union of the graphs of the inequalities. And so when we talk about union, we're talking about bringing the two pieces together. And think about a union, right? We talk about a marriage is a union between two people. And so union is bringing it together to make it one. And so let's look at a statement here that is an OR statement and see how that's going to graph. So we're going to use a similar statement to one that we did in the first problem, but we've changed a couple things. So x is greater than 5, or x is less than or equal to 2. And so we've done the same thing. We've drawn 3 graphs here because we want to see what's going to happen as we mold these together into one graph. And so x is greater than 5. So at 5, we're going to have our circle, and it's going to shade towards what? 6, right? Because 6 is greater than 5, and so there's my arrow going that way. And then we do the same for x is less than or equal to 2. What do I put at 2? A dot. And where's that going to shade? Towards 1, because 1 is less than or equal to 2. And so my shading will go this way. And there's that. Now, remember what we said about union, right? The 2 become what? 1. So we don't lose anything in between. We just pick up everything that both have. And so when we draw this graph, the 2 becoming 1, I take this segment over here and I keep everything that it had. And I take this piece over here and keep everything that it had. And so now it creates my purple. But here, again, we don't see that an overlap where they're going to make the red and blue make purple. It's just that each piece goes together and we draw what was there. And so what are the solutions here? Well, 0 would be a solution. Now, 0 is not greater than 5, but 0 is less than or equal to 2. And this is an OR statement. So remember what we talked about. The OR can be exclusive, where it's one or the other, or it can be inclusive, where it's both. And so in this case, this OR allows me to be exclusive, and it works in the one statement. It works here. As long as it works for one statement, it works for the entire compound inequality. Now, what's another solution? Well, 6 would be a solution, right? Because 6 works for the first statement. 6 is greater than 5. It doesn't work here. 6 is not less than or equal to 2. So again, it's only got to work for one statement with an OR. So that's what we're talking about when we talk about and OR problems. So now we're going to look at translating some of these statements into inequalities, being able to graph them, and being able to solve them. So let's go to that. So in example 1, we're going to have a couple of examples here where we're going to translate the verbal phrase into an inequality, and then we're going to graph it on the number line. And so in statement A, we've got all real numbers that are less than -3 or greater than or equal to 5. So let's take a peek at the two statements that we have. First off, which word are we going to have in the middle? We're going to have the word OR. So let's write that down. OR. So I'm going to have a statement here and a statement here combined by the word what? OR. Now, don't get too caught up on this part. All real numbers, all that means is that any value that fits, right? Because we're talking about a part of the number line. And so when we see that phrase, that's just our variable. That's our x. Now, what's the next piece? It says all real numbers that are what? Less than -3. And so in that statement, I'm going to have x less than -3. And then we're going to do the other statement. And so we're going to come over here, and I've got greater than or equal to 5. And so we're going to write that statement. X, because again we're dealing with real numbers, that are what? Greater than or equal to 5. And so those are our two statements that are combined by the word OR. Now, we looked at the previous example in the definition that we did 3 graphs. But with an OR graph, do I really need 3 graphs? No, because each piece is just going to stay on the graph anyways. And so I'm only going to draw one number line here. Now, on the previous problem, we went from 0 to 6. Remember that I talked about having to just use your critical values. So I'm going to put my -3 on the graph. I'm going to put my +5 in the graph. And then I'm going to put a number to the left of the -3, in between the -3 and 5, and something to the right of 5. So I'm going to have 5 values on this number line. So something to the left would be -4. Something in the middle here is 0, and something to the right is 6. Doesn't have to be perfectly spaced. We're just writing out the number line. So, what are the two statements? X is less than -3. So that's a circle at -3, and -4 would be less than -3, so it shades this way. The other statement, X is greater than or equal to 5, so that's a dot at 5, and 6 is greater than 5, so my shading will go towards 6. And so remember, it's just those two pieces on one graph is the final graphed solution. That's it. So don't overcomplicate it. Again, if it's an OR problem, draw one line, put your two critical values, pick some numbers on each part, and then figure out where the graph's going to be. Now, most OR graphs are going to look like this. They're going to go out in two different directions. There are exceptions to the rule, and we'll talk about those exceptions to the rule as we need to. But understand, whatever happens, so like if I have both graphs going this way, or both graphs going this way, it's an OR statement. And so it only has to be true for one piece or the other. It doesn't have to be true for both. So just keep that in mind as we look at some other examples. So let's go down to example B. All right, so let's look at example B. All real numbers that are greater than or equal to -5 and less than 4. And so our keyword that is and so we're going to write that. And then we're going to talk about the two pieces. So the first piece, so again, we got the statement all real numbers. That's just our what? That's our X for both problems. And then it says what? Are greater than or equal to -5. So my first statement, X is greater than or equal to -5. My second statement, less than 4. So again, starting with the X is less than 4. So I've got my two pieces. Now, again, if you're more comfortable drawing this in 3 separate pieces like we did the first definition, that's great. I'm going to show you a little shortcut to this, not getting around any rules, but just understanding where things are going and where things are going to overlap and not have to draw as much. So, I'm going to draw my number line. And again, my critical values will go on it. -5, +4. I need something to the left, so that's -6. Something in the middle, 0 here, because between negative and positive would be 0. And to the right of 4 would be 5. And so we're going to graph the two pieces. And remember, we want red and blue to make what? Purple. Now I've got green and blue, so obviously that analogy doesn't work perfectly, but we want the two to be where they overlap. Now, how would I graph X is greater than or equal to -5? Well, that would be a dot at the -5. And where would that shade? To the -6 or to the 0? Well, 0 is greater than or equal to -5. So this would shade this way, right? Now, we're not going to put the shading on there yet. We're going to get there in a minute. Now, let's do the other one. X is less than 4. So what's going to happen at 4? I've got my circle at 4, right? And then where's that shade? Towards 0 or towards 5? Well, 0 is less than 4, so that's going to shade this way. And so where's the overlap going to happen? The overlap happens in the middle, because as the blue keeps going to the left, right? As the blue keeps going this way, it's going to go past that -5. But only blue's out there. And as the green keeps going to the right, it's going to go past 4. And only green's out there. The only place where the green and the blue overlap in this problem is in the middle, right here. We keep the circles, we keep the dots on an and problem, and we shade where the two overlap. That's it. Okay? So, pay attention to the statements. Now, one thing that we can do, we can rewrite the statement actually as one simplified inequality. I'm going to show you that real quick on the side here. And so we have the statement X is greater than or equal to -5, and X is less than 4. Another way to write this statement, watch this. Remember we talked about how we could flip this inequality all the way around, and it will also flip the sign. And so I can rewrite this as -5 is less than or equal to X, and X is less than 4. Now, we're going to take this and smush it like a sandwich, because now I've got these X's in the middle, right? We're going to smush it together, and I'm only going to have one X in the middle. And so it's going to be -5 less than or equal to, all of this is going to smush together and just become an X. And then I've got the less than 4. And so this statement and this statement are the same. I do not care how you write it out on a problem like this. What I do care about is that you know if you see the statement down here as one conjoined inequality, it's an and statement. Or if you see it like this, obviously it has the word and in it, but they both mean the same thing. And so when we graph something like this, we see the -5, we see the +4, and we can see what symbols they would have with them. And the x is where? In the middle, because -5 is less than some x value, and that x value has to be less than 4, and that creates that middle zone there. All right, so let's look at the next thing. So in example C here, a bucket truck has a bucket that sits on top of the arm, so like an electrical truck, right? And the bucket's maximum height is 30 feet, and the minimum height is 6 feet above the ground. Write and graph a compound inequality that describes the possible heights of the bucket. And so if you're, again, kind of picturing this, so we've got our bucket truck, right? Here's our truck. And it has a bucket on it that's able to extend its arm up, right? And it says it has a maximum of 30 feet and a minimum of 6 feet. So this is our max, and this is our min. Which means that the bucket can go where? Anywhere, what? In between. Now, let me give you a little hint here. They told us which type of inequality this is going to be. Right here. Because it used the word and. And so our maximum height, so our height has to be what? Less than or equal to 30, right? And we talked about these phrases. Maximum was in those words that we talked about in section 2.5. Go back to that, right? And so h is less than or equal to 30. And what? If we come back over here, the minimum height is 6 feet. And so h has to be what? H is greater than or equal to 6. We could write it the other way as well. Sorry, I'm not jumping on y'all. Come on now. 6 is less than or equal to h is less than or equal to 30. And again, we can flip this around and get it to where the h's are both in the middle in our statement. We always go from small to the middle to the large when we write a statement like this. And so drawing our number line, here's the 6, here's the 30, 0's to the left of 6, 10's in the middle, a lot of values in the middle here, and 31's to the right of 30, right? And so drawing this out, what do we have at 6? We're going to have a dot. At 30, we're going to have a dot, and my shading is in between, because the bucket can be any height between 6 feet and 30 feet. Okay? So again, pay attention to what statements are given, pay attention to the wording, right? Like we talked about maximum or minimum, and then be able to graph that inequality. So let's take a look at a couple that we're going to solve, and that'll be it for this video. So in example 2, we're going to look at solving compound inequalities that are given to us. And so in the first example here, we're asked to solve and graph 7 less than x plus 5 is less than or equal to 15. This is an and problem because remember we've got this sandwich here, right? We've got a left, a middle, and a right. Now, typically when we talk about solving, we talk about what we do to one side, we have to do to what? The other. But I don't have 2 sides here, I've got 3. And so what I do to one side, I've got to do to all 3. Left, middle, right. Now, here's the key. We want the middle piece to have the variable in the end, just the variable. So what do I have to do to get just x or y or whatever variable we're dealing with, just that variable in the middle? Well, in this case, what would I do to get this x by itself? I subtract 5. But remember, we're going to do that where? Left, middle, right. And so I'm going to minus 5 over here. I'm going to minus 5 over here. So again, left, middle, right. And so 7 minus 5 is 2. The inequality doesn't change here because we just subtracted. That part cancels, leaves our x. Less than or equal to, that gives us 10. So we have this solved now because the x is in the middle by itself. We're done. Okay? And so now we're going to graph this. And so draw our graph. Here's 2. Here's 10. To the left of 2 is 0. In the middle we got 5. And to the right we've got 15. And again, what other numbers you choose are your choice as long as they make sense. You know, we don't want to put a number that's not between 2 and 10 in the middle there, right? We want a number that's there. And so at 2, I've got a circle. At 10, I've got a dot. And my x is in the middle. My inequalities make sense. So my shading will be in the middle. Okay? So again, pay attention to what is going to go where in the end. Let's look at example B. So in example B here, we're given 3x minus 5 is less than or equal to 13, and x minus 3 over 2 is greater than 9. And so we're going to solve both of these pieces and then have to graph it on the number line. And so we'll solve the first piece first. Do these two things separately and then bring it together in the end. So 3x minus 5 is less than or equal to 13. So I'm going to add 5 to both sides. So I get 3x is less than or equal to 18. And then we're going to divide by 3, and so x is less than or equal to 6. Now, still got that word and that's going to come down. And when we look at the second piece here, x minus 3 over 2 is greater than 9. We're going to multiply both sides by 2 first. Because remember, if I've got that fraction, I've got to get rid of the denominator first before I can get rid of everything else in the numerator. So the 2 and the 2 will cancel. X minus 3 is greater than 18. We'll add 3 to both sides, plus 3 and plus 3. So x is greater than 21. So there's my two statements. Okay, so x is less than or equal to 6, and x is greater than 21. Watch what happens when we graph this. Now I told you there's going to be special cases, right? So 0 to the left, 6 in the middle, we can do 15 there, right? And then 21, so let's go 25. Think about the two pieces here, right? So I've got my first one in green. X is less than or equal to 6. Well, so that's a dotted 6 shaded towards what? Towards 0, because 0 is less than or equal to 6. Okay? And then my second piece, it's a circle at 21 and shaded towards the right, because 25 is greater than 21. Okay? So in this case, it's an and problem, right? So is there an overlap? No. So in the end, there is what? No solution, because neither of these pieces overlap, so there is nothing on this graph that's going to work. There's not a value that works for both of these at the same time and completes the statement. Okay? So again, pay attention to what happens, because like I said, there's some cases where sometimes it doesn't go the right direction and we don't get a solution. Okay? So one last example and then we're done. So on the final problem here, we're going to solve and graph x plus 8 is less than 5, or 3x is greater than or equal to 12. And so we're going to do each piece, right? But be cautious, we have the word or here in between this time, right? So we're going to solve the first piece. X plus 8 is less than 5. What are we going to do? We're going to subtract 8 from both sides and get that x is less than negative 3, right? And then we're going to do the same on the other side. So we've got 3x is greater than or equal to 12, which means I'm going to divide both sides by the 3 and get that x is greater than or equal to 4. And so in this problem, it's an or problem. So remember, we just take the two pieces, put them on one number line, and we're done. Now, again, special cases could come up, but in this one, this is not a special case. So we've got our negative 3, we've got our positive 4. To the left of negative 3 is a number like negative 5. In between negative 3 and 4 is 0. And to the right of positive 4 would be, let's say, 10. So as we graph this, my first piece in orange, x is less than negative 3, so that's a circle at negative 3 shaded towards negative 5, because negative 5 is less than negative 3. And then same on the other side. X is greater than or equal to 4, so that's going to be what? A dot at 4 shaded towards 10, because 10 is greater than 4. And so again, make sure you get your two pieces on the graph, and that's it. So in this section, again, we talked about how to write compound inequalities. We talked about how to graph and solve them. So make sure you pay attention to that. Make sure you fill out the Google form for this section, and I will catch y'all next time.